A car is driving on a circle on a road made of ice. I don't think that's recommended in real life, but you know what? It's physics problems. They don't need to make sense. So we are trying to find for the first problem, what is the radius of the turn if the road is banked at 20 degrees? So we need to write down our knowns. We know that our tangent velocity is equal to 16.6. Let me just make it better. 16.67 meters per second. It says 60 kilometers per hour. I just plugged it into Google and they spit out the mass in meters per second. Our theta is going to be 20 degrees. Our radius is unknown. We're trying to solve that. And then our mass is 800 kilograms. Draw a quick free body diagram over here. Engineer's best friend. So the car is going to have a normal force pointing at some direction. This road is banked 20 degrees and it's going to have a weight force going straight down. So in order for the net force to point this way, since it's going in a circle, the y component and the weight component must cancel out. So this next point is going to be better illustrated on a dot. That is the wrong way. The weight is always going to point straight down to the center of the earth, but since the normal force is at an angle, we're going to need just the y component right here. But how can we figure out the y component of normal? Well, we can just take the tangent. So tangent of theta is equal to the opposite, so it'd be nx over the adjacent. So yes, over the adjacent. My bad. We need to find nx because that's pointing towards the center. And nx is right there, and y is right there. Since y's need to cancel, and ny needs to go to the other side, and ny is also equal to w. So w times tangent of theta is going to get us nx, which is what we need. That's the net force pointing towards the center of the circle. And since now that we got the net force pointing towards the center of the circle, we can figure out the radial acceleration, which is also the tangent velocity squared divided by the radius. And that's the thing we need right there. The radius has showed up in one of our equations. So our radius is equal to the mass times the velocity squared divided by nx, and nx is equal to w tangent. So we got mass times g, which is the w, and then we got the tangent of theta. Yeah, that's awesome. Masses cancel out. Mass never matters. They always cancel out. And so we got 16.67 squared divided by gravity times tangent of 20, which is going to get us 77.9 meters. So the main problem with this one is trying to figure out the x component. And since the normal y component must equal the weight component, so that way they cancel out and the net force points straight towards the center of the circle, you can use tangent of nx divided by ny and substitute w in for ny in order to use values that you already know. And then you can just rewrite and do algebra for the rest until you isolate r, and you get 77.9 meters for part A. Part B, The ice has now melted on the road, and there is now a static friction force on the road and the car tires. What is the minimum value of the coefficient of static friction between the tires and the road required to prevent the car from slipping? Assume that the car's speed is still 60 kilometers per hour and the radius is the one that we calculated. Okay, so now the car is on level ground. So we have the normal force going up, the weight force going down, and then we got a friction force pointing towards the center because the car needs to have a net force going this way in order for it to go in a circle. So our friction force is equal to our mass times the radial acceleration, and then simplify these down to their components. So we got the coefficient of static friction times the mass times gravity, because the normal force is mass times gravity, and the normal force times the static friction is equal to the static friction force, is equal to mass times velocity squared tangent divided by the radius. Guess what? Masses cancel out as usual. So our coefficient of static friction must equal the velocity squared divided by r times g, which gets us a static friction coefficient of 0.364.